Imagine standing just a few feet away from a river of glowing metal that's hotter than the lava erupting from some volcanoes. One wrong move could mean disaster, yet skilled workers handle it with incredible precision every single day. Most people see a finished engine block, a massive ship propeller, or a heavy construction machine, and never ask where it truly began. But here's what nobody tells you. Almost every one of those parts was once nothing more than liquid fire. Think about this. Metal casting is one of humanity's oldest manufacturing technologies. Yet today's factories use robots, artificial intelligence, and laser scanners to perform a process that began over 5,000 years ago. We are about to step inside foundries where temperatures exceed 1,600 degrees Celsius, machines shake entire buildings, and molten metal transforms into precision parts worth millions of dollars. And this is where it gets truly extraordinary. Today, you'll follow every step of this incredible journey, from iron or buried deep underground to the finished castings used in cars, airplanes, wind turbines, heavy machinery, and even spacecraft. You'll hear the thunder of giant furnaces, feel the heat of molten metal, and discover engineering secrets that most people never even imagine. What happens inside these factories surprised even experienced engineers. Everything begins beneath the Earth's surface. Iron ore comes from massive mines in Australia, Brazil, India, Canada, and South Africa, while aluminum originates from bauxite deposits in Australia, Guinea, China, and Brazil. Copper, nickel, chromium, manganese, and silicon travel from mines scattered across every continent. Every casting starts with a carefully engineered recipe that determines its final strength and performance. Most people never think about this, but producing 1 ton of high-quality cast iron can require well over 1.5 tons of raw, or before refining even begins. Massive crushers reduce boulders larger than family cars into small fragments before magnetic separators remove unwanted rock. Conveyor belts stretching for kilometers carry millions of tons of material every year. The refined minerals travel thousands of kilometers by freight trains, cargo ships, barges, and heavy trucks before reaching modern foundries. Some shipments cross entire oceans, taking weeks before arriving at their destination. A single delay at a busy shipping port can stop an entire casting plant within hours. The global supply chain operates with astonishing precision. Inside the foundry, engineers blend virgin metals with carefully sorted recycled scrap. In many factories, recycled material accounts for over 70% of every melt, dramatically reducing energy consumption and carbon emissions. Spectrometers analyze every batch down to fractions of percent because even tiny changes in chemistry can weaken the final casting. Precision starts long before the furnace is switched on. Environmental responsibility has become one of the industry's greatest challenges. Modern foundries recycle sand, recover waste heat, filter airborne particles, and reuse thousands of tons of scrap every year. Some facilities recycle more than 95% of their molding sand, dramatically reducing landfill waste while lowering production costs. But the real magic begins only after the raw materials disappear into the furnace. Now everything changes. Within minutes, solid metal weighing thousands of kilograms will become a glowing liquid hotter than molten lava. Giant induction furnaces will unleash enough energy to melt steel like butter, while engineers monitor every second with incredible precision. And what happens inside those furnaces is one of the most spectacular sights in modern manufacturing. The moment the raw materials enter the induction furnace, everything changes. Powerful electromagnetic coils generate intense heat, raising the temperature to approximately 1,550 to 1,650 degrees Celsius, 2,822 to 3,002 degrees Fahrenheit. For steel, and around 1,350 to 1,450 degrees Celsius, 2,462 to 2,642 degrees Fahrenheit for cast iron. Within 45 to 90 minutes, thousands of kilograms of solid metal transform into a glowing liquid brighter than the midday sun. The roar of electricity, the shimmering heat, and the smell of hot refractory brick fill the entire foundry. But here's what nobody tells you. Molten metal isn't ready for casting the moment it melts. Engineers carefully remove impurities floating on the surface, known as slag, before adding carefully measured alloys like chromium, nickel, silicon, manganese, or molybdenum. Digital spectrometers analyze the chemical composition in less than 60 seconds, ensuring accuracy within fractions of 1%. A tiny mistake here could ruin an entire batch worth hundreds of thousands of dollars. While the furnace prepares the metal, another team builds the molds that will shape it. High-pressure molding machines compress specially prepared silica sand mixed with bentonite clay and water at pressures reaching 80 to 120 psi. The mold becomes incredibly strong, while remaining easy to break apart later. Every cavity reproduces details accurate to within plus or minus 0.2 millimeters, capturing shapes that look impossible to cast. Complex castings require sand cores built separately using resin binders hardened at nearly 220 degrees Celsius, 428 degrees Fahrenheit. These fragile-looking cores create internal passages for engine cooling channels, hydraulic systems, and hidden cavities impossible to machine afterward. Workers position every core by hand because even a single millimeter of movement can destroy the finished casting. Human experience still wins where robots struggle. Now comes the most breathtaking moment in the entire factory. Overhead cranes carry giant ladles holding up to 20 tons of molten metal across the foundry floor. The liquid glows white-orange as temperatures remain above 1,500 degrees Celsius, sending shimmering waves of heat into the air. Every movement happens slowly because one sudden motion could create dangerous splashes capable of melting solid steel. The pour itself lasts anywhere from 20 seconds to several minutes, depending on the size of the casting. Molten metal rushes through carefully engineered runners and gates before filling every corner of the mold. Engineers calculate flow rates, turbulence, and cooling behavior using advanced simulation software long before production begins. Watching liquid metal race through the mold feels almost like watching glowing water freeze into solid rock. Then comes the waiting. Depending on the casting, cooling may take 30 minutes, several hours, or even an entire day. As the metal solidifies, it shrinks slightly. So engineers design feeder systems that continuously supply additional molten metal to prevent hidden cavities. Most people never think about this invisible process happening deep inside the mold. Once the casting cools enough, giant vibrating shakeout machines begin their work. The entire mold shakes violently, breaking away the hardened sand, while revealing the newly formed metal part hidden inside. Dust fills the air as conveyor systems separate reusable sand for recycling. What emerges still looks rough, but its final shape is already there. Powerful robotic saws and plasma cutters remove runners, gates, and feeders before automated grinding stations smooth every surface. Massive shot blasting machines fire thousands of hardened steel pellets every second, stripping away oxidation and leftover sand. The once black casting emerges with a clean metallic finish, ready for precision machining. The transformation feels almost magical. At first glance, the casting looks complete, but the toughest challenge still lies ahead. Engineers now have to prove that no invisible cracks, air pockets, or structural weaknesses exist anywhere inside the metal. Finding flaws hidden beneath a solid block of steel requires technology that almost seems like science fiction. And that's exactly where we're heading next.